Unit 3, pages 57 and 62, Empirical Analysis. The formula of a compound can be deduced by chemical analysis. When the percent composition by mass of the atom measured experimentally, the formula can be calculated. Remember that one of Dalton's laws said that all molecules of the same compound have the same ratio of atoms. The ratio of atoms in the molecule must be the same as the ratio of moles in a large sample. Example 3.19. Experimental analysis finds that the percent composition of mercury in HgXCl is 73.9%. Determine the empirical formula. So first of all, the mercury makes up 73.9% of the HgXCl, but how much of it is made up of chlorine? Well, remember, combined, these must equal 100%. So if we take 100 minus 73.9, we get 26.1%. So together, these equal 100%, the total compound. And so there's a little rhyme that we've been taught to help us find the empirical formula. Percent to mass means literally just change the percent sign to grams. Mass to moles. So I'm going to convert both of these to moles. I have to go to the periodic table and get the mass of mercury in order to convert it to 1 mole of mercury. And mercury is essentially 200 grams on the periodic table. And then chlorine here is 35.45 grams, which will equal 1 mole of chlorine from the periodic table. 73.9 divided by 200 gets us 0.368 moles of mercury, and 26.1 divided by 35.45 gives us 0.735 moles of chlorine. So now I want to divide them each by the smaller of the two, and the smaller of the two is 0.368. 0.368. This is going to equal 1, which tells me that there's 1 mercury in the formula, and this is going to equal 2, which tells me there are 2 chlorines in the formula. And so we have an empirical formula of Hg1Cl2, though we don't normally write the 1. Remember that this is an empirical formula. All we know is that the ratio of mercury to chlorine is 1 to 2. We do not know what the true molecule looks like. It could be Hg5Cl10, which is a 1 to 2 ratio also. Since this molecule is ionic, the actual crystal will have many mercury atoms and chlorine atoms, but the ratio will be 1 mercury for every 2 chlorines. Recall the crystal structure of NaCl here, where you're going to have 1 of each, but they're set up in such a way that they are staggered and there are many sodiums and chlorides present. For the interior atoms in this crystal, each sodium is surrounded by 4 chlorine atoms, 8 atoms in 3 dimensions, and each chlorine is surrounded by the same number of sodium atoms. The empirical formula is the simplest ratio of atoms, or NaCl. So exercise 3.20, a compound is found to have the following composition by mass. We'll have 62.1% carbon, or go ahead and change the percent to grams, 5.21 grams of hydrogen, 12.1 grams of nitrogen, and 20.7 grams of oxygen. So remember, percent to mass, we want to determine the empirical formula. We're going to do mass to mole. So each of these is going to be divided by its mass from the periodic table in order to turn it into moles. And so since I know this, I could more quickly just divide by the mass from the periodic table. This is 14.01 and this is 16. But make sure you understand why we're doing this in short. The dimensional analysis shows you more that we're converting from grams to moles, and it is okay to do the shortcut where you take the grams, divide by the molar mass, because that does yield moles as well. So once I divide each of these masses by the molar mass, I'm going to get these amounts for the moles for each of them. So now that I've done percent to mass, mass to mole, I want to divide by the smallest of these, which in this case is 0.8638. So all of these is going to get divided by 0.8638, and that's going to end up giving me hopefully some sort of whole number. Here I'm going to get 6 carbons. Here I'll get 6 hydrogens. Obviously this is 1 for nitrogen, but when I divide this by this, I don't actually get something that's going to be easy to round to a whole number. I actually get this, which is so perfectly in between, I'm going to have to call it 1.5. And so we're going to put 1.5 oxygens here. So my formula so far is C6H6, 1 nitrogen, and 1.5 oxygens. We're going to have to keep the 1.5. However, we don't want to permanently keep it, so in order to get rid of a half, you simply multiply all of your subscripts by 2, and that'll get rid of the half, and so we end up with an empirical formula of C 2 times 6 is 12, H 12, N 2, and 2 times 1.5 is going to equal 3. And so this is our final answer. There's that fourth step in our rhyme that says multiply till whole, and that's where you're going to get a molecular formula from the empirical formula. The actual molecular formula can be found from the empirical formula by comparing the mass of the empirical formula to the mass of the molecular formula. So here is the molecular formula C2H2, in which the simplest ratio between 2 to 2 is 1 to 1, which means this must be in the empirical formula. Notice that if I multiply this by 2, that gets me to my molecular formula. Also notice that this mass is twice as much as this mass, and so that's how I know that my molecular formula is double what my empirical formula is. The table shows an actual molecular formula and the simplest whole number ratio of atoms described by the empirical formula. Since the molar mass given is twice the mass of the empirical formula, the actual molecular formula can be found by multiplying the subscripts in the empirical formula by 2. Another way to describe this idea is the actual molar mass, or the molecular formula mass, divided by the empirical molar mass, or empirical formula weight, is going to be equal to an integer. The actual molecular formula is found by multiplying the subscripts in the empirical formula by the number n. So once I compare the molecular mass divided by the empirical mass, I'll get a number, a whole number, has to be a whole number, times, and I'm going to multiply that times the empirical formula, and that'll give me my molecular formula. So for example, for CH, the actual mass is 26, but if I do carbon plus hydrogen, that's 12 plus 1 equals 13, and when you compare those, you get an integer of 2, and that means 2 times the CH gives me my molecular formula of C2H2. Here's your note card for this section. Keep in mind that an entire compound must be equal to a total of 100%. So if you're missing a percentage, consider that if everything together is 100%, then you can figure out the missing percentage. Finding empirical formula, you're going to do percent to mass, that's change the percent sign to grams, then convert from mass to mole. You can just take the grams you have from here and just divide by the molar mass in the periodic table, and then take the moles, divide them all by the smallest moles that you solved for. And that's going to give you a ratio, and that's going to be our empirical formula ratio. Be careful if you end up with 0.5, you have to keep it 0.5 and then double everything. And it is actually possible not only to get a 0.5, but to get either a 0.67 or a 0.33, in which everything would get multiplied by 3, as opposed to here, everything is multiplied by 2. So that's a possibility to look out for. To get this last step, multiply till whole, that's how I convert my empirical formula to a molecular formula. And I do it by comparing the mass of the molecular formula divided by the mass of the empirical formula. It's going to be the larger mass divided by the smaller, because you should always end up with an integer greater than 1, or 1, or greater. And then you're going to put that integer here and multiply it to your empirical formula, and that's going to bring your subscripts up to be the correct molecular formula. The empirical formula is the simplest whole number ratio. The molecular formula is the true formula.